And from page 41, in the case of number 87, I held off on this one, okay, since there are quite a few steps involved in the sense of taking apart a big collective entity. And in the case of number 87, okay, we have multivariable expression, okay, where we have among the terms we have 7y cubed z minus 40 y to the second z to the second minus 12 times yz cubed and looking at ultimately factoring by grouping. First of all, before we go into this stage, we look to see if there is a greatest common factor other than 1. And if you notice among the terms, while 1 is the highest number that will go into the coefficients 7, negative 40, and negative 12, all of these terms do share at least y and z terms of the various degrees. So we have, for what we have in y, we at least have y to the first. And likewise for z, we have from the first term a first order factor in z. So the highest term, or the greatest common factor that can be taken completely into this whole trinomial, is going to be yz. And for what we have upon factoring out yz, we have dividing yz into 7y cubed z. Okay, so you have 7 y into y cubed is y squared, and z goes completely into itself. And then we have for the next term yz into negative 40 y to the second z to the second. Okay, we have negative 40 yz, and for yz into negative 12 yz cubed, okay, we have negative 12. Y goes completely into itself. As for z into z cubed, okay, we have negative 12 z squared. And setting the stage for complete factorization, now we have yz, and the rest of the factors will come from the factoring by grouping of 7y squared minus 40yz minus 12z squared. And just putting a bit of the activity over to the side. So working with this factored out trinomial, once again looking at factoring by grouping, multiplying the first and the last coefficients, we have 7 times negative 12, which will be negative 84. And looking at factors of this product whose sum will be at negative 40. Again, we started out with 7 and negative 12, and that's not going to be the combination of the coefficients that will be used to split up negative 40 yz. For the sum of these values will be at negative 5. So we are again looking at numbers that will multiply into negative 84, and that will add up to negative 40. So we're going to have more weight applied to the minus part than to the plus. And for this combination, okay, we're going to have negative 42 and 2. Negative 42 times 2 is negative 84. Simultaneously, negative 42 plus 2 is negative 40. So we have with this trinomial we're going to split up the negative 40yz into separate terms. And technically it does not matter which term you have at the front, but I like to have the positive coefficient term to follow, and that is going to be ensured that the middle operation is addition, and I will not have to do any sign modification that would otherwise be required if I had the operation of subtraction to be located in the middle. So for what we have in this situation, we have 7y squared minus 42yz plus 2yz minus 12z squared, and where the grouping will come in. So if I cluster together the first two terms inside parentheses, so I have 7y squared minus 42yz. Again, we have the operation in the middle. It's going to be addition. Again, if I had switched the order, the middle operation would be subtraction, and I would have to envision grouping together the last two terms, factoring out -1. But with the plus, I don't have that added burden, so I'm at liberty to just go ahead and duplicate the 2yz minus 12z squared. And looking at drawing out the greatest common factors, okay, now we have with the first pair, okay, so the highest term that will go into these will be 7y, and taking into 7y squared minus 42yz, we're going to have y minus 6z followed by the addition. Now for 2yz minus 12z squared, okay, we're going to have 2, and z is shared in the group, and taking into this last pair, okay, we also come out to y minus 6z So for what we have in the result, okay, so we're going to have a quantity. Okay, so we have y minus 6z, which is shared in common, and the other is going to be formed by the outside terms in operation, which we will have at 7y plus 2z. So this completes that part, and so putting it all together, we have with the problem itself, again, we had drawn out yz, the greatest common factor, and then factoring out this trinomial. We have in factored form, we have yz times the quantity of y minus 6z times the quantity of 7y plus 2z. And that is the complete answer. Now, picking up where we had left off last time, we started looking into rational expressions and operations. And for what we have in the next section, in section R4 on page 51, okay, for this set, we're looking at simplifying expressions. And there's a part that is asking for what are regarded as the restricted values. And for what we have in the case of number 17, we're looking at simplifying x squared minus 9. And we have all over x squared minus 4x minus 21 And looking at simplifying, so we have in the numerator is the difference of squares. In the factors, we have x plus 3 and x minus 3. For what we have in the case of x squared minus 4x minus 21, if I factor, again, x squared goes to x and x. And factors of negative 21, whose sum will be negative 4. This will signal that more weight will be provided for the minus end than for the plus. So we're going to have, in this case, x minus 7 and x plus 3. Negative 7 times 3 is negative 21. Negative 7 plus 3 is negative 4. And looking at what we have in the factored forms of both the numerator and denominator, we have a common expression in both the numerator and denominator with x plus 3, so we can get these to go out. And for the completely reduced form, we're going to have x minus 3 all over x minus 7. Now for the other parts, we're looking at what are regarded as restricted values. And what we mean by a restricted value, this is a value that we have, in this case for x, that will cause the rational expression to be undefined. Now, how can a fraction be undefined? Well, the rule of thumb is that in the case of fractions, the bottom number can be any real value except for 1, and that exclusion is 0. So you can divide by any number but 0. So you cannot have a 0 denominator. And we're looking at the restricted values to be anything that causes the original form of the ratio to end up with a 0 denominator. So for this fraction to be defined, the restriction is that x squared minus 4x minus 21 cannot be 0, and if this cannot be 0, neither can its factors. So we have, in terms of the restricted values, if we look at x minus 7, that cannot be 0. And if x minus 7 cannot be 0, then we have that x cannot be equal to 7. Alright, now if we look at x plus 3, if this cannot be 0, then we have that x cannot be negative 3. So we have, in the case of the restricted values, it does not matter what order you place them. You can say negative 3 and 7 are restricted, or you can place in the order that you see them. And to give you a bit of a quick visual, and we have, say, going over to Desmos. And looking at the ratio. So again, we had x squared minus 9 all over x squared minus 4x minus 21. And just looking at what we have in the ratio, and I will pull up a table. Okay, notice you have for the input values, you have negative 2, negative 1, 0, 1, and 2. None of those values are restricted. So for these inputs, you're going to have some defined value for the ratio. I could go with, say, like 10. That's not restricted. 9 is not restricted. 8 is not restricted. 7, on the other hand, is restricted. And this input causes a zero denominator, so you have an undefined statement in this case. Now 6 is not restricted, so there is a defined value. So 7 is restricted. Now for the input 0, okay, your denominator will be -21, so there is a defined element. -1 is not restricted. -2 is not restricted. -3 is, and thus you have with the input value of -3 for x, you have the zero denominator, and the readout would be undefined. So -3 and 7 are the only two amounts that you can place into x and end up with this particular original ratio to end up being undefined. Now, for what we have in the case of the next item, okay, the nature of the problem, very similar to what we have in 17. And this time we're looking at the variable y. And for the ratio, we have y squared minus 64. And we have all over y squared minus 7y minus 8. And just looking at reducing, we have the factors of y squared minus 64. Yet another difference of squares, where the factors, we have y plus 8 and y minus 8. For y squared minus 7y minus 8, okay, if we factor, again, just like x squared goes to x and x, y squared goes to y and y. And factors of -8 with a -7 for the sum. We have -8 and +1. And just as x plus 3 was common to both numerator and denominator in problem 17, we have here y minus 8 as a common factor between the numerator and denominator. And for the completely reduced form, okay, would come out to y plus 8 all over y plus 1. Okay, now in terms of the restricted value or values, again, we're looking at the values that will cause the denominator of the original form to be equal to 0. And one might ask, okay, could you not start out with the reduced form? And the answer to that is no. And while in one sense, like in terms of proportions, these are the same, but in terms of every aspect, they're not exactly the same. And this is going to be a future topic where we will be dealing with all kinds of asymptotes, like the vertical asymptotes, the horizontal asymptotes, the slant asymptotes, and there will be some of the restricted values that will form asymptotes, and there'll be others that will have holes in the graph, and there's a fine line that separates these, and this is going to be a future topic, which I think is going to be in either chapter 2 or chapter 3. Okay, so the restricted values, you're going with what you have originally, not what you end up after reduction. All right, so for the original denominator, okay, so we have y squared minus 7y minus 8 cannot be 0. Once again, we have with the factored form, we have y minus 8 times y plus 1 cannot be 0. Itemizing once again, each of the factors cannot be 0. If y minus 8 cannot be 0, okay, we have that y cannot be equal to 8. If y plus 1 cannot be 0, okay, we have that y cannot be negative 1. And those will be our two restricted values. And if you were to put the whole ratio into your calculator or Desmos, you might have a table of input values for y, okay, where 10 is good, 9 is going to come out to a ratio, 7 will come out to something, 6 will come out to something. But if you input 8, you're going to have that undefined message. And likewise, you would have the very same thing if you were to input negative 1 for y. Now, in the case of operations, some of you might have had encounters with cross multiplication between fractions. And we have for the next item, okay, such a potential case. And for 28, okay, we're doing more than just factoring. Okay, we're looking at multiplying ratios together. And the ratios we have, first of all, is the fraction 8x minus 3y over x cubed y to the fourth. And we have times the second fraction, which we have at 6x y to the eighth, all over 24x minus 9y, and some of you might be able to see some of the cross multiplication in advance. And if you have done that, that's fine. We'll just sort of take this gradually, step by step. For what we have in the binomials, we have 8x minus 3y, and there is no common factor other than 1. For 24x minus 9y, this one can be factored since we do have 3 as the greatest common factor. And looking at what we have here, upon rewriting the first ratio, we have 8x minus 3y again, all over x cubed y to the fourth. Okay, we have 6x y to the eighth. Now for the denominator of the second ratio, okay, we're going to factor out 3. And this will be times the quantity of 8x minus 3y. And if you notice between the numerator and denominator positions, we have 8x minus 3y shared in common. So we can reduce, and you could also simultaneously reduce 6 over 3. You could do both operations in one sweep, but we'll just do it gradually. So for what we have in the numerator, okay, so you have 1 times 6x y to the eighth, and we have all over 3 times x cubed y to the fourth, and we have for 3 will go into 6 2 times. Now for what we have regarding x and y, we have different degrees in x and y in the numerator denominator layout. So for what we have in x, if I completely reduce and display the variables in positive exponential terms, okay, so between the x factors, okay, you have the higher degree at the bottom. And just for the standalone x, you read this as if you had x to the first, and for y, the higher power resides in the numerator. And if we look at reducing, okay, so you have 2. Now for what we have for x, so we have x to the 3 minus 1. For what we have in the case of y, so we have the higher power in the numerator, and the reduction stays in the numerator. So we have 2 times y to the 8 minus 4 and so we have for the end result, we have 2 times y to the 4th, and we have x to the 3 minus 1, so this will end up at x squared. Okay, so for the completely simplified form with positive exponents in the variable, it would come out to 2 times y to 4th all over x squared. Now, in terms of doing a little bit of combining of addition as well as simplifying, we have this time in a different variable. In number 41, we have with the letter m and the nice thing about this problem is that we have the same denominator in both ratios. So we have m squared all over m plus 3. And the other ratio we have at 6m plus 9. All over m plus 3. We have the same denominator in both ratios, and we can go ahead and combine the numerator terms. So you have m squared plus 6m plus 9, and we have with the numerator now consisting of all 3 terms. This can be factored, and this is one of the special cases of where we had to exist a squared trinomial for m squared plus 6m plus 9. Okay, this will factor to m plus 3 times itself, and in the completely factored form we have nothing but m plus 3 in the numerator and denominator. And so we have shared a set of m plus 3 expressions between the numerator and denominator. So I can get the denominator out by canceling out one of the m plus 3's in the numerator. And so for what we're going to have here, upon reduction, okay, this comes out to the direct expression, which we will have at m plus 3. So the sum of these fractions comes out to a direct expression. Now, for what we have in the case of combining fractions that do not have the same denominator. Now, the other day we had touched upon briefly prime factorization. And for what we have in the case of number 43, we have such a potential case. And in this one, both ratios are in the letter C. So you have 2 over 9C plus 7 all over 15c cubed. All right, so we got 9c, 15c cubed, got different degrees in the variable c. 9 and 15 are not the same number. And if we look at both of these denominators through prime factorization, okay, so we have the coefficient 9, okay, the prime factorization of 9 is going to be 3 times 3. For what we have in the case of 15, Okay, 15 will factor out to 3 times 5. So we have 3 and 5. Both of these are going to be prime factors. And for the variable factor, we have only the letter C. Now looking at the least common denominator, we're looking at the greater or greatest number of appearances of each of the prime factors among the prime factorizations, like we have with 3. 3 appears once upon factoring out 15, and it appears twice from factoring out 9. So you have more appearances from factoring 9 with the number 3 than you do with the number times 3 appears from factoring out 15. So we're going to have a couple of 3's. For the number 5, it doesn't even show up at all from factoring 9, but it does show up once from 15. And as for the letter C, you're looking at the highest degree representation of C. And in this case, this is going to be C to the third. Okay, and the reason I'm having C cubed in the least common denominator. Least common denominator, greatest common factor, not the same thing. Now the greatest common factor of C and C cubed would be C, but for the least common denominator, look at it this way. C will go into C cubed can go into itself, but if we reverse, you cannot take C cubed into C directly. All right. So for the smallest term that both 9C and 15C cubed will go into, this will end up being 45C cubed. And looking at what we have now, we've got 2 over 9C. And if I adjust this ratio in terms of the least common denominator, okay, so you have 9 will go into 45, 5 times. C will go into C cubed, C squared times. For 7 over 15C cubed, we already have the cube of C, and for this second ratio we need to multiply by 1 in the form of how much 15 goes into 45 divided by that amount. So 15 into 45 is going to be 3, so we're going to multiply this second ratio by 3/3, and just taking what we have now. Again, we have both of the denominators are adjusted to 45C cubed, and combining the numerator terms, we have 2 over 5C squared, which we will have at 10C squared, and we have 7 times 3 is 21, and so we have for this final outcome, okay, we have 10C squared plus 21 all over 45C cubed. Now, we're going to look into the next problem, but I tell you what, just on the page working with prime factors. Let's see what we get for combining ratios in exact form. So let's see what we get in the result whenever we have 1 over 40 plus 1 over 100 minus 1/18. So let's see what exact fraction we get in simplest form without the decimal, and we'll discuss in the next few moments. Okay, so looking at getting things set up, okay, we have 1 over 40 plus 1 over 100 minus 1 over 18. And if we look at the prime factorization, 40, 100, as well as 18, now we have, in the case of 40, you can pick any combination of factors that would go into 40 outside of 1 times 40. You could go with 2 times 20, 4 times 10, 5 times 8. What do you say we have 4 times 10? Okay, neither 4 nor 10 will be a prime number, for 4 can be factored out further, not just 1 times 4, but also 2 times 2. 10 is the same way, not just 1 times 10, but in prime factorization terms, okay, we have 2 times 5. So in prime factorization form, 40 reduces to 2 times 2 times 2 times 5. Now for the number 10, several different ways you can factor, like 2 times 50, 10 times 10, 4 times 25. We'll just say we have 10 times 10. And once again, each 10 will factor out to 2 times 5 times 2 times 5. And if I just arrange in order from smallest to largest, okay, so 2 times 2 times 5 times 5. Yes, 100, thank you. That's what happens when you zoom in too much. Zoom in and zoom out. Thank you. Okay, so we have in the case of 18. Okay, various ways you can factor out 18. Okay, you can go with 3 times 6 or 2 times 9. And we have for 2 times 9, okay, 2 is a prime value. 9 goes to 3 times 3. So for what we have here, okay, we got the prime factors. We have 2, 3, and 5. As for the least common denominator, okay, so we're looking at the greatest number of appearances up to from any one of these factorizations. Okay, so from 18 it appears once, from 100, okay, it appears twice, and from 40, okay, this will appear 3 times. In the case of 3, it doesn't appear at all from 40, nor does it appear from factoring 100, but it does appear twice from 18. So you're going to have a couple of 3s. And as for 5, okay, it doesn't come at all from 18. It comes once from 40, but the greatest number of appearances of 5 comes from factoring out 100. So that is going to appear twice. And if we multiply everything together, okay, you have 2 times 2 times 2 is 8. And you got 3 times 3 is 9. You have like 8 times 9 is 72. 5 times 5 is 25. And 72 times 25, this is going to come out to a 4-digit number with 1800. And this signals that 1800 is the smallest value that all of 40 and 100 and 18 will go into. And modifying, okay, these ratios, in terms of the least common denominator, so that I will be able to combine them into a single fraction. So 1 over 40, and we'll multiply by 1 in terms of the number times 40 will go into 1800 over itself. So 40 into 1800 will be 45. For 1 over 100, 100 goes into 1800 18 times. And for 1 over 18, 18 is 1800 is going to be 100. So we have multiplying the last ratio by 1 in the form of 100 over itself. And looking at combining, okay, you have 40 times 45, 100 times 18, 18 times 100. So you have, again, the least common denominator of 1800. Now for the numerator products, okay, we have at the front, we have 45. We have plus 1 times 18, which is 18. Now we have subtraction. Subtraction of 1 times 100, so we are looking at subtracting 100 and looking at putting everything together. We have 45 plus 18 will make 63. In turn, 63 minus 100 comes out to negative 37. So we come out to negative 37 over 1800. And the result might seem a little bit surprising, for with the fractions like 1 over 40, 1 over 100, as well as 1/18, okay, those are pretty much small fractions, but typical small fractions. But for the result here, one could probably say that it is anything but typical, but sometimes whenever you're looking at adding and subtracting, sometimes the cookie can crumble in unexpected ways. And I think this is such a case here. Now, looking at going back to fractions with variable denominators. And we have for number 48, and this problem presents a little bit of a different case. Here we have 4 over m minus 2 minus 3 over m and one bit of distinction is that we had the least common denominator, which would be the smallest expression that both m and m minus 2 will go into. It would just happen to be the product of these denominators. Okay, so you have m times the quantity of m minus 2. And if we translate what we have here in terms of the least common denominator, so we have 4 over m minus 2 and adjusting. First ratio has the m minus 2 part of the least common denominator, and it needs the m. So the first fraction is going to be multiplied by 1 in the form of m over itself. We got the subtraction. Now for 3 over m, okay, this has the m portion and it needs the m minus 2 part. So the second ratio will be multiplied by 1 in the form of m minus 2 over itself. And for what we have in terms of the follow through. Okay, so now we were going to have both denominators to be identical at m times m minus 2. Now in terms of the numerators, okay, now we have 4 times m, so we're going to have 4m. Now in the case of the second set, we have subtraction, and we got a 3. We have times the quantity of m minus 2. And I'm going to distribute furthermore in the numerator. Okay, so with the denominator still at m minus 2, or m times the quantity of m minus 2, we have at the top we have 4m, and for the next part of the numerator we have negative 3 over the quantity of m minus 2. So negative 3 times m, we have negative 3m, and then we have negative 3 distributed over negative 2 is going to be a plus 6. So we have 4m minus 3m is m, and we have plus 6, and we have all over m times the quantity of m minus 2, and that will be the result upon combining these ratios, where we had started out with 4 over m minus 2 minus 3 all over m. All right. Now, in the case of what we have also with the partaking of sums and differences of fractions. Now we've done quite a bit of changing up with the variables. Okay, we've been going from like the typical x and y, then changing up to like letters like C and M, and now we have the letter T. And for what we have in the case of 52, now we have 3 ratios in the mix. And here we have 5 over t squared, and we have plus 4 over t plus 2. And we have minus 3 over t. Okay. Now, we have different denominators, but we can go ahead and identify what the least common denominator is going to be. If you notice, we have standalone expressions in the letter t. We have t squared and t, and one part of the least common denominator is going to be the higher degree representation of just the letter t. So that is going to be at t squared. Same thing here like what we had earlier when we worked with 9c and 15c cubed. Again, the least common denominator, you go with a higher degree representation of the variable, and that was c to the third. I can take c into c cubed, but you cannot take c cubed into c. Same parallel, you can take t into t squared, but you cannot take t squared directly into t. And for what we have with the other part of the least common denominator, that is the only binomial denominator we have, and we have that with t plus 2. So the least common denominator is going to be t squared times the quantity of t plus 2. And adjusting the fractions, so 5 over t squared, this has all of t squared, it now needs t plus 2. But what we have next, we have 4 over t plus 2 Okay, now that one has the t plus 2 portion, and it needs t squared. So you got subtraction. Now in the case of 3 over t, this is a little bit of a different scenario. Okay, now first ratio cover all of t squared, second ratio cover all of t plus 2. But in the case of the last ratio, you don't have either portion completely covered. Okay, so with t and to cover the rest of t squared, so t into t squared is going to be t, and you still have the t plus 2 to also deal with. So this last ratio will be multiplied by 1 in the form of t times the quantity of t plus 2. So looking at combining the terms, okay, so you got t squared times t plus 2 throughout in the denominator. You got t squared t plus 2, t squared t plus 2, t times t is t squared, and you still have over t plus 2. For the numerators, 5 times the quantity of t plus 2, so this will be 5t plus 10. And we have plus 4 times t squared. And for the rest, I'm going to take this a step further. We got subtraction. We got negative 3 times t. Times the quantity of t plus 2. So we have 5t plus 10 plus 4t squared, and we have with the remaining group, we have negative 3t over the quantity of t plus 2. Negative 3t times t is negative 3t squared, and negative 3t over 2, this will be a negative 6t. And we have, upon consolidating, and you can put the numerator terms in most any order, but I like to put them with the highest degree at the front. So highest degree we have in second order, so you got 4t squared minus 3t squared, so this will be t squared. And we have for the first order terms, we got 5t and negative 6t, so this will make negative t, and of course we have the standalone constant with 10, and so we have for the final result, okay, this will end up being t squared minus t plus 10 all over t squared times the quantity of t plus 2. And again, throughout we'll be looking at ratios, factoring, as well as just combining all kinds of like and unlike terms. And now we're going to cross over to not just combining terms, but also working with equations. And there are some categories here. And for what we have in section R5, okay, there's a part that mentions categories. And the ones of interest, okay, we have with conditionals, you also have a contradiction, And also we have with identity. And looking at each of the categories. Now, most of the ones you'll be encountering will be the conditionals. And a conditional is going to be an equation with a limited number of solutions. Like you can have like a problem where there is only one solution, or some might coin as one right answer, and that would be a case of a conditional. And in the realm of algebra, say if you're looking at solving for x, and say we have, in this equation, let's say we have 2x, or 2 times x, plus 5 is equal to 17. Okay, so this would be a case of a conditional. Okay, so we have, for x, the value must be on the condition so that once you take 2 times it and then add 5, it should come out equal to 17. And so we have for this particular equation, if you solve, and there are ways that you can go about this, and common way is to isolate the 2x. So we can take 5 away from both sides of the equation. So left hand side we have 2x, and on the right we have 12. And with 2x equal to 12, we can undo multiplication by 2 upon dividing by 2 throughout the equation. And 2x over 2 is x, 12 divided by 2 is 6. And so this statement, 2x plus 5 is equal to 17, will ring true on the condition that the value of x is equal to 6. So this is a sample of what you have with a conditional. Now for a contradiction. A contradiction is going to be an equation that has no logical solution. We can have like a setup where the result is trying to say that two things are the same when in fact they are different. And a case here of what could be a contradiction. If we look at trying to solve for x, and we'll say we have 2 times the quantity of x plus 3 minus 4 is equal to x plus 5 and looking at solving for x. Okay, so if we simplify this equation, we can go ahead and distribute the 2 over the binomial x plus 3. So we have 2x plus 6, followed by the subtraction of 4. To the right, we have x plus x, which will make 2x. And we have plus 5. And we got 2x plus 6 minus 4. So we have 2x plus 2 is equal to 2x plus 5. And in terms of combining like terms, you can either eliminate one constant or variable expression. So what we'll look at subtracting 2x. Okay, so if I subtract 2x on both sides, what's going to happen here? We got 2x minus 2x. You have 2x minus 2x. And guess what? There's no x term left standing. So for what you have remaining, 2 is to the left, 5 is to the right. And guess what? In between we have equal. And this statement says that 2 is equal to 5. And of course that is not a true statement. So that means that whatever you try to plug in for x, whether it is a 0 or a positive number or a negative value, there's no way that both sides are going to be able to equal each other. And so in this case, there is no solution. And in this particular capacity, okay, this is a contradiction. Now for the third category, okay, we have what is regarded as an identity. And for an identity, okay, we have in this particular case, right, this is the, whether it's going to be a conditional or a contradiction or an identity, this is going to be the category in the trio that's going to have not a limited number of solutions or no solutions, but an infinite number of solutions. And for what we have just as a sample of what could be an identity, we can say we have 3 times the quantity of x plus 4, okay, is equal to x plus 6 plus 2 times the quantity of x plus 3. Okay, so we have, again, gathering the variable terms and constants. Now we have on the left 3 over the quantity of x plus 4, so this would be 3x plus 12. And to the right we have x plus 6. And with the next distribution we got 2x plus 6. So I have 3x plus 12. To the right, x and 2x will make 3x. 6 and 6 will be 12. If you notice, we have the left and right hand sides to consist of 3x plus 12. And let's say that if I were to combine the variable terms. So if I take 3x away from both ends of the equation, okay, just like in the prior case, okay, we've got two numbers left standing, and this time we have 12 is equal to 12. Before we had two different numbers that were said to be equal to each other, and now with this statement we have this to end up being true for 12 is equal to 12. So this is a case of an equation that turns out to be an identity. And for this scenario, we're going to have for x, we have an infinite number of solutions. And what I mean by this is that whatever you have for x, it could be 0, it could be a positive value, it could be a negative value, and both sides will always equal each other. And there are notations you could write for this. Okay, some like to use a capital R, or write out all real numbers. And there's one other notation. This is going to be what is going to be regarded as interval notation, where you have parentheses around negative and positive infinity. So these are three different ways of saying that the solution to x will be the set of all real numbers and this particular case again is an identity. Again, conditional a limited number of solutions, contradiction no solution. In the case of an identity, okay, you have an infinite number of solutions. Now, in the case of equations, one we're going to be looking at time and again, not only in terms of equations, but also in terms of the functional capacities, and that's going to be centered around the word quadratic. And for what we have in the case of quadratic equations, again, there are various ways that you could write this, but for a quadratic equation, okay, you're going to have a second order equation. Second order equation whose standard form is going to be ax squared plus bx plus c is equal to 0. Okay. And we have that a cannot be equal to 0. Okay. Again, so we have with second order equation, especially stressing the second order, so you're looking at stressing the degree of the variable x. Okay, and if a happened to be 0, guess what? There would not be an x squared term, and this equation will no longer be second order. Alright, now in the case of solving equations that are quadratic, okay, there are varieties of techniques that can be utilized. And if we had the coefficients to be just right, we can use what is referred to as the zero product property. Now, the property is often introduced with the interaction between two terms, but let me state that this is not limited to just two terms. It could be, in fact, an infinite number of terms, but just putting it in terms of just a couple of terms. If we have that the terms a and b are such that a times b is equal to 0, then we'll have that either a is equal to 0 or b is equal to 0. Right, so if a is 0, we got 0 times b is 0. And if it is b that is 0, we got a times 0, which is still going to be 0. And one might say, okay, I see in both of these forms you have equal to 0, but I don't see any x squared or any of that in the a or b. So how do those relate? How does this equation and this property relate? Okay, well, as cases here, to shed light on the situation, if you have, let's say, in solving for x, and we'll say we have x squared plus 7x plus 10 is equal to 0. So we have x squared plus 7x plus 10 is equal to 0. And we've had kind of an exposure with the zero product property, and this is back when we were looking at what could not be equal to 0 with the restricted values when we were working with the fractions from the start of the section. But with the zero product property, we're looking at equaling 0. And if we go from this trinomial to the factored form, and it doesn't matter what order you place these factors, I'll just say that we have x plus 5 times x plus 2 is equal to 0. And symbolically, okay, you can say that, okay, we have two expressions, and we can say here with these two terms, we can say that a is represented by x plus 5 and that b is represented by x plus 2. So if this expression is 0 and we have the product that results to be equal to 0, then one of these factors must be 0. So at the one end, it could be that x plus 5 is equal to 0, or it could be x plus 2 is equal to 0. And if we have that x plus 5 is equal to 0, we're going to have that x is equal to negative 5. If, on the other hand, it is x plus 2 that is 0, we have that x is equal to negative 2. And this equation would be a case of a conditional. And what I mean by this, again, a limited number of solutions. So this equation will ring true on the condition that we have x equal to either negative 5 or negative 2. And you can go back and check. Now we have a negative 2. So you have negative 2 squared, or the square of negative 2, is going to be 4. 7 times negative 2 is negative 14. 4 minus 14, or 4 plus negative 14 is negative 10. Negative 10 plus 10 is 0. For negative 5, again, the square of negative 5, or negative 5 times itself, is going to be 25. 7 times negative 5 is negative 35. 25 minus 35 is negative 10. In turn, negative 10 plus 10 is 0. And so those are going to be our two solutions in this case. All right. Now, another case of the zero product property. Now, let's say if you have an equation that is not provided in standard form yet. Okay, so let's say we have x squared plus 36 is equal to 12x. Okay. And for what we have here, now we don't exactly have the standard form. They've got the ax squared at x squared, and have c at 36, but you got the bx at 12x, not on the same side, but across the equal sign. And so we'll just fix this and have this equation set equal to 0. So I'm going to move the 12x over. And so we're going to have situated. Okay, so we got x squared minus 12x plus 36 is equal to 0. And if I factor this trinomial, x squared goes to x and x. And we have factors of 36 that will add to negative 12. We have negative 6 and negative 6. And if you notice, we have x minus 6. Okay, you got a repeating factor. With x minus 6. First case, the factors were distinct, and we were able to draw out two different values in the solution. But since we have with x squared minus 12x plus 36, which ends up as a squared trinomial, we have only x minus 6 as a factor, and so there's going to be only one solution, and that is going to be with the number 6. And just one more portion here regarding the zero product property. Let me show you just a couple of things here where how would you treat, let's say, a common factor that is a coefficient. Okay, there are a couple of ways here. I'm going to show you both of these. It will seem redundant, but I just want to mention this in case there's like a problem in ALEKS that says to solve for the variable and you had the presentation already in factored form. Say you have negative 2x squared plus 8x plus 64 is equal to 0. So I'm just going to put this down twice. Okay. Now one approach, okay, if you look at rewriting the first term where you have it to be x squared, okay, so if we look at the approach, say if we factor out negative 2, so if I factor out negative 2 to get the first expression in line with just x squared. So you have negative 2 into negative 2x squared is going to be x squared. Negative 2 into positive 8x is a negative 4x. Negative 2 into 64 is a negative 32. So you have this trinomial to arise, and we can factor this. So we have with x squared, okay, this will go to x and x. And with negative 32, okay, we have factors of this number that will add up to negative 4. We have more weight with the subtraction than the addition, so we have x minus 8 and x plus 4. So we have a negative 2. Okay, this is just a coefficient. It's not doing anything with x, like in terms of directly adding, subtracting, multiplying, or dividing. So this is just a coefficient, and it is not going to be a solution in x, since it is, strictly speaking, not an x factor. But these other two are. So we have x minus 8 is equal to 0, and x plus 4 is equal to 0, and with x minus 8 equal to 0, you have x equal to 8, as well as x equal to negative 4. And so we will have the possible solutions here will come out to 8 and negative 4. The reason I'm mentioning this is like if Alex had presented the problem like in terms of solving for x, and it started out with this situation, I've seen it several times, like something along the lines of they get these x values and then they have to throw in a third solution with -2, but we're not working with x where it is interacting with -2. -2 is just like a dummy coefficient. It's not doing anything for us in terms of solving for x. And in terms of the same problem, if you had this to encounter, not starting with this step but that one, you just go ahead and divide by -2. Again, you can still factor out -2, but if I were to go ahead and divide by -2, you would just have x squared minus 4x minus 32 is equal to 0. We're just dividing by a number. There's no x factor we're dividing by, and the follow through is going to be history repeating itself. Yeah, so again you have x equal to 8, as well as -4. Okay. So you'll have somewhat different approaches, but both of them are correct, and the results are also correct. Okay.